Hello, welcome to your virtual lesson for today. Super strange being in this classroom and talking to a computer and doing the lesson to none of you guys right now. So we're going to see how this goes. I can't wait to get your feedback on whether you liked this or you didn't. I can't imagine doing an entire unit this way, but maybe some lessons here and there. It'll be nice to individualize your time kind of working with the material. Since this is a video, you will be able to pause and fast forward and jump backwards, rewatch as many times as you need to. So take your time with this. Hopefully it won't last too long. I'm hoping to use kind of the timer on my computer to gauge how long this video is going to be. But you are going to be on page 277 in Agile Minds today. So you are going to be working on this page right here. It's called Modeling. You're going to work through the notes. You're going to work through them with me right now individually. You have headphones in. You're on a Chromebook. And once you finish, once you get all the notes, there's going to be a little bit of a link to respond to. And that's just how I'm going to check that you got those notes and you finished through the video and you were able to respond to my final question after you watched the whole lesson. Your homework will be up on the board tomorrow. So you will be able to apply what you learned in this little mini lesson to the homework and hopefully be able to get started. We'll continue to work with this material once we finish through all the tests come Thursday when we fully start Unit 8 and we walk away from Unit 7. But until then, this is how my classes that are meeting for 30 minutes are going to learn. So gather with me on page 277. We're kind of just going to break this down a little bit. So the first piece of this is we're trying to figure out what the best fit model is. What is our best fit model? And it gives us three options here: linear, quadratic, and exponential. And so with those three, what allows us to decide that? So if you are given a table and it is linear, it means that there is a constant number being added or subtracted. So you're going to have something that's being added to every y value or subtracted from every y value. Then if it is quadratic, you're going to know that the second difference is constant. Or you're going to notice that reflective pattern. You're going to notice that vertex with the reflection and the symmetry happening on the left and right sides of it. So you might find symmetry. The last one is exponential. So for linear, we have a constant number being added or subtracted. For exponential, it's actually a constant multiplier. So I'm going to let you copy that down. You can pause the video right here and make sure that you get those definitions down on your paper. And then we're going to move on and we're going to apply that to three tables so you better understand that. So as I move down here, it's giving us three different tables. So now I kind of want to show you what I mean when we are looking at a table. How do we decide whether it is linear, quadratic, or exponential? Which one would model it the best in terms of your actual graph? So if we're looking at this first one here, you're going to notice that each of these terms are actually being multiplied by 4. So I'm multiplying everything by 4 to find my next y value. So 1/16 times 4 gives me 1/4. 1/4 times 4 gives me 1. 1 times 4 gives me 4, and so on. A constant multiplier means what? Linear, quadratic, or exponential? Exponential. For our second chart here, if we're looking at what we have up here, I'm kind of looking at it, and what I'm noticing is that every single time, I'm actually adding 2. Negative 2 plus 2 equals 0. 0 plus 2 equals 2. 2 plus 2 equals 4, and so on. So if my reasoning is adding 2, I have a constant addition that's occurring, I know that it's linear. So now here's my last one. So I told you could find your quadratic in two ways, the second difference, or you can look to see, do you see that symmetry property that's occurring here? So if we're looking right here, we're kind of gauging that a little bit, and let's think about what the difference is here. So 2 minus 9 gives me negative 7. Negative 1 minus 2 gives me negative 3. 0 minus a negative 1 gives me positive 1. I'm not noticing something constant there, so now I'm going to take it to the second difference. Negative 3 minus a negative 7 actually gives me 4. The difference between those numbers is plus 4. 1 minus a negative 3 is really 1 plus 3, which is, again, a difference of 4. So now what I'm seeing is there is a constant difference as my second difference. So since the second difference is constant, I know that it's which of the three. Look back at those first three definitions. Is it a constant addition or subtraction? Is it a constant second difference? Or is it a constant multiplier? You should note that it's a quadratic. It has a constant second difference. So right now you could pause the video and you can make sure you get this as that next. We're going to continue moving through this. So now another way to go about this is just kind of thinking about it in terms of words. So if I didn't give you a chart and I just gave you a sentence, could you tell me whether that was going to be modeled by a linear function, a quadratic function, or an exponential function? So we're going to start by looking at A, B, and C today. A says that a golf ball is hit and lands 10 seconds later 320 feet away. Whenever anything is being thrown or is being kicked, it's going to have a similar pattern to it starts on the ground, it goes up, and then it lands on the ground somewhere else. When you see that pattern of rising up and coming back down, what do you think of? Maybe you said parabola. That is our quadratic. So whenever you see something being thrown or kicked, that oftentimes is modeled by a quadratic. So now let's look at B. We have a math class that's ordering donuts for a party in which the cost for a party box is $2 and each donut is 50 cents. That's something that is constant. You pay the $2 for the party box, and for every donut, you're going to increase by 50 cents. So it's kind of like saying your y-intercept is $2. Initially, you have to get the party box. It's $2. For every donut you buy, you're going to be charged 50 cents. So 50 cents becomes your slope. That's modeled by something linear. And now let's look at C. C says Daisy opened up a lemonade stand during the summer. She took all of the money she had earned and opened a savings account that earns 6% interest compounding continuously. If you ever see anything about doubling, tripling, compounding continuously, that means that it's going to increase by 6% every single time. So you take something, you take 6% of it and add it in. And now you have a new total, and you take 6% of that. That new total is bigger, so 6% is actually going to be bigger in that new total, and you're going to add more to it. So the longer you have something in the bank that's compounding by 6%, it's going to be compounding a lot of money one day because the total is going to continue to get bigger. So that becomes a constant multiplier, which puts us at an exponential. Give those last two another try, but those are the three that I want us to have as examples. Remember, these notes will be posted up on Canvas, so you will have everything worked out for yourself. So now let's look at something like this on the next page. It says in a random sample of 1,000 people ages 5 to 25, it's found that their age and their annual income were strongly correlated. So that's something we're going to define here soon, that correlated word. It's talking about a relationship between two things. So let's look at these two statements. Would it be correct to say that growing older causes a person to earn more money? Or would you say that it's earning more money that causes a person to grow older? Hopefully you said it was the first one. Hopefully you know that it's not the amount of money increase that you have that you grow older. Some of you guys might be making better pay per hour than the person sitting next to you right now, but it's not making you any older. It just happens to be the job that you have. However, why would it be that as you grow older, you have a higher income? Probably because you have more experience, or because you've been more reliable at that job, or you've been there for multiple years and there's an increase in pay every single year that you're there. A lot of jobs will work that way. So that's why we would say that yes, it would be correct to say that as you grow older, oftentimes your annual income is going to increase for a various amount of reasons. So now we come to this word called correlation. Correlation can either be positive or it can be negative. For a correlation to be positive, I almost want you to think of a positive slope. You're thinking of something that moves in a positive direction, low to high. If something has a positive correlation, it means that they're moving in the same direction. So if something is increasing and it causes the other to increase, that means that it's a positive correlation. They're both increasing. However, it's a negative correlation if as one increases, the other decreases. I want you to think of a negative slope. Over here, you have a really high y value and a really low x value. As x gets bigger, your y is getting smaller. They're moving in the opposite direction, so this is very similar to a negative slope. I'll show you what that looks like in some examples. If you go to number 5, we're going to look at A and B today. For A, it says the number of energy drinks someone drinks and how long that they can stay awake. So let's think about that. The number of energy drinks that someone drinks. We're going to say that as that increases, so as the drinks increase, does it allow you to stay awake longer or does it make you go to sleep? It allows you to stay awake longer. So the hours you are awake goes up. There's more hours that you can stay awake. A lot of times in college, people will drink a lot of energy drinks when they have the test the next day because they're trying to stay up and pull an all-nighter so they can cram and crash and study for that test. Not good study habits. Don't develop that here, and also don't do it in college. But oftentimes you'll see people just drinking all the energy drinks they can drink or drinking a lot of coffee so it keeps them awake longer. That would be a positive correlation. Not because that's a positive lifestyle choice, but because they're both increasing. One is increasing, the other is increasing. Look at something like B, the temperature outside and how many coats and sweaters one wears. So let's think about that temperature. You could think about it in two ways. As that temperature increases, as it gets warmer and warmer and warmer outside, do you wear more coats or do you wear less coats? You wear less coats. The amount of layers that you're wearing is decreasing. Less coats. Someone may think of it the other way. As your temperature decreases, so as it gets colder, right now we're headed into the winter. As it's gotten colder, have you worn more layers or less? You've probably increased your layers. Do you see how as one increases, the other is decreasing? That causes the negative correlation. So test out C and D. See if you can decide if one is increasing, the other increasing, or is it decreasing? Do they have a positive correlation or a negative correlation? All right, here we are again. Here's just another refresher. on is this linear, is this a quadratic, or is this exponential? If we look at these three, you will notice that my first one, all of these are adding 5. I'm adding 5. What do we say when we have something that's constantly being added? Linear, correct. Let's look at 7. I see that 2 times 3 gives me 6. 6 times 3 gives me 18. 18 times 3 gives me 54. If I have a constant multiplier, what am I? I'm exponential. And for this last one, I actually want you to look more at the symmetry this time. So one time we figured it out with the second difference, but now if we're looking, think about these points. We have -2, 0, -1, -3, 0, -4, 1, -3, 2, 0. Right now, I've made a pattern that looks like that. This 0, -4 being my vertex. That looks a lot more like a quadratic because of that symmetry pattern. You can pause the video right now and you can make sure you get these down. Don't forget that as I go through this video, I know it might seem to be going quickly. You have the power to pause. You have the power to re-listen to anything that I said to make sure that you get these notes down. So if you need to pause right here and rewind and go back through the different reasons, or if you need a moment to just kind of pause so you can copy this down on your paper, please do so. Move at the pace that you need to move today through these notes. So this right here is actually going to be the last thing that we come back to. So number 9, we're going to skip over right now and we're going to come back to that. I'm sorry. This is what happens when this is live. Right before we jumped here, right before we jumped to the identify the type of function, linear, quadratic, or exponential, there's this bolded word right here that says correlation coefficient. I'm sorry, I skip over it. I always forget that it's written right there. The correlation coefficient, that's going to be really important. That's also known as the R value. This number tells us what we know about the correlation, whether it's positive or negative. So here's the way we're going to break it down. Here's your number line. You're looking at the numbers -1, 1, and 0. Your R value has to be between these values. It has to be between -1 and 1. It could never be over 1. It could never be bigger than 1. You could never have 1.0000956. You would never have that. You might have 0.999999999 repeating. Sure, that works, but not over 1. And the way that it breaks up is this tells you if it's strong and if it's positive or negative. -1 means it's a strong negative correlation. Strong negative. So what do you think positive 1 means? It's a strong positive correlation. It's a strong positive correlation. So if it's a strong positive correlation at 1 and a strong negative correlation at -1, 0, what do you think 0 is? In the middle. It's neutral. It's not strong, it's not a strong negative, it's not a strong positive, it's just kind of weak. It's weak and it's neither. The closer you are to 0, whether you're positive or negative, means the weaker your correlation is. It's not strongly correlated. And then whether you're closer to a positive 1 or a negative 1 tells you, is it positively correlated? Are they both increasing? Or is it negatively correlated? Do they have opposite relation? One increases and the other decreases. Okay, so we are starting to get to about 20 minutes with this, and I also want to know that we only have 30 minutes to get through class today, and I wanted you guys to be able to pause this video and get the notes. So we're going to actually stop there. So what we should have been able to discuss today, I'll do a little brief overview. Today in class, we should have discussed that in order to decide whether your best fit is linear, quadratic, or exponential, we knew that something being added or subtracted constantly was going to be linear. Quadratic was going to be a constant second difference. So the second difference you take between your y's will be constant, or you'll see that symmetry pattern. Or exponential, a constant multiplier. So you can find that by looking at the relationship down your y columns. We talked about how you could read a sentence and decide, is this have a pattern that looks like a quadratic, something being thrown or kicked? Is it doubling? Is it tripling? Is it increasing by 6% annually or compounded annually? That's a multiplier, therefore it would be exponential. Or does it have that y-intercept with a constant increase in how many things you're adding to your bundle or your total? That's going to be linear. Then we talked a little bit about causing. And how maybe that correlation doesn't necessarily imply causing, okay? They could work differently. It could be, even though they're both increasing, one's not causing the other. We talked about that correlation. If the correlation or the relationship between two things is positive, that means that as one increases, the other will increase. We talked about that correlation being negative. So if one thing increases, the other thing is decreasing. We learned how to read a sentence and decide whether it was positive correlation or negative correlation, deciding on are they both increasing or are they inversely related, one's increasing, one's decreasing. We discussed this correlation coefficient, that R value. It's going to always be between -1 and 1. It tells you whether you're strong or weak, and it tells you whether you're positive or negative. So if you're weak, you're going to be close to 0. If you're strong, you're close to your 1 or your -1. If you're a negative number, you have that negative correlation. If you're a positive number, you have the positive correlation. And lastly, we just took a moment to kind of do that one more time, decide which table was showing us what, linear, quadratic, or exponential, based on the reasoning we know. So the last thing that I want you to do today is actually use a slip of paper, and I want you to do your best to define in your own words correlation, causation, and correlation coefficient. You can give me an example, or you can write it in your own words. However you can best describe that today after working through this lesson and getting the notes. I want you to tell me, which one of these do you feel pretty good about? Which one do you not feel that great about? Do your best to define them in your own words. What does it mean to be a correlation? What is causation? And what is that correlation coefficient? Look back at your notes to help you come up with a definition, and thanks for sticking around today. I'm looking forward to hanging out with you guys in person on Thursday and doing an all-group lesson. But I hope that this was fun and this was a cool way to kind of individualize today.